Okay, so it's 5:30. Your exam is right here. If you haven't picked it up, you can come here and pick it up. We have a couple of people who haven't picked up their exam. I'm pretty sure you have seen your grades on online. I've already posted all of the grades online, except for a couple of people who stayed here after the exam. I didn't remember their grades, so I gave them their exam. I gave them the paper. So make sure to, if you were here after the exam, I graded the exam for you, make sure to tell me what your grade was, okay? Because I have to put it on Blackboard. And I'm not sure about the university's policy, but I think I have to hold on to your exams just for future records. So you can keep on, you can hold on to them. You can like go over them for a week or so. Just bring it back to me, okay? And the exam average was for undergrads was 70, while for graduates was 73, which is a pretty decent average for the 578 for this class. Yeah, let's actually start with question. Is there anyone who has any? Pick up your exam. Your exam is right there. You can pick it up. Is there anyone in class who has a question? Yes.
So, like, if we answered all 3 questions, they just dropped the lowest question?
That's what I did, yep. That's right. But if you have a specific question, it is possible that I've made a mistake, right? So I actually, that happened. One of the graduate students reached out to me, and I graded his exam for him, and I had to increase his grade 20 points. So this happens, right? So make sure.
Like, I had done all 3 questions before you said that we didn't have to do the 3rd one, and I got like half the credit, but they dropped it because it was like the lowest. Does that make sense? Like, that was like.
Yeah, I was the one who graded this exam. So they graded, yeah. And we can talk about your specific case after the class, okay? I don't remember what happened there. And okay, but so the exam, I assume no one is satisfied with their exam performance. I am not satisfied with your exam performance as well, because in my mind the exam was I don't want to say easy, but it was not hard. It was a so-so exam. It had some like the problem number 12, I guess. A lot of people got it wrong, which was a very huge surprise to me. Yeah, a lot of people got this problem wrong, which was a huge surprise because it was the easiest problem you could get. Just find the curl of velocity, right? So, but it was lengthy. Coming in, I expected to give you, I was expecting myself to give you at least half an hour of extension, right? Which probably, and I mean, we could have made it shorter. So I assume everyone agrees that the exam could have been shorter, right? Okay, so this is what we're gonna do for the next exams. Let me actually tell you a little bit of reasoning. The reason we had this many questions, and the reason I expected to give you some extension on time was because the exam was open book, right? Open Note, Open Google, and one of the students actually obviously cheated and used check.com and all of the other resources, because I know how their solution goes, right? So I wanted to avoid that. That's why I gave you a lot of questions, but short answer questions except for problem number 1. But I don't think it's going to work because it's a lot. It's the burden is going to be on people who are not going to cheat, and they are going to have a hard time in the exam. So this is what I'm going to do for the next exam, exam 2, and the final exam. We are going to have just a one-sided letter size equation sheet. That's the only thing you are allowed to bring to the exam, which essentially means that you're going to get less questions, fewer questions, and easier ones, right? Because you don't have that many resources. So if you know the material, you should be able to ace the exam, right? That's the idea. And for the online students, just to level the playing field, you have to be online during the exam time. I mean, all of you are in class, so this is a message for online students. You have to be, again, you have to be online during the exam time, and you have to turn on your camera, because it is not fair to all of you who are in class. I mean, I have to have some sort of a check on them as well, right? So does this make sense? So just to avoid any unfairness, if you will, online students have to be online during the exam time. They have to turn on their camera, so I can make sure, at least as much as I can, as much as possible for me, I can just make sure they're only using a one letter size, two-sided, whatever, cheat sheet, equation sheet. And that equation sheet, you can like include all of the concepts, and that's what I did every year. That's what I do for all of my classes, actually, except for this one. And and if you are not satisfied with your grade, exam 1 grade, don't worry about it. What we can do for you is to use the final grade for this one, right? So if you feel like you know the material and you could have done better on this exam, but for whatever reason you didn't, there can be millions of reasons, right? If you do well on your final exam, I'm going to use that grade for this one, right? Does this make sense? I think that's a fair deal, right? And the final exam is going to be comprehensive. We can refine the terms of the agreement later on, but that's essentially what I'm planning to do. Okay. If you're also someone who has done well in this exam, but they want to get an A instead of a B plus, the offer extends to you as well. This offer extends to everyone in class, not just people who have done poorly on their exam. Okay. So I guess this should resolve, hopefully, any problem you may have had with the exam. Okay. So that's for the exam policy. But let's talk about the exam itself. The questions I included on the exam, most of them, like the descriptive ones, I distinctly remember in class when I was talking about this, I told you that this will be a part of the exam. This is very important, like center of pressure, all of those things. And I really like, specifically for a couple of them, like the center of pressure or the dynamic and the path line, the streak lines, all of those. What is this? Like a couple of problems, I really expected everyone to get it right, because you have your lecture notes. They were part of the lecture notes. And I saw some people going through, like, control F-ing through to the book PDF, which tells me that you haven't studied, right? If you have to control F through book. So make sure you study when you come to the exam. If you do so, I'm pretty sure you'll get it right. And if you know what to ask, and if you ask me the right question, you will get a very helpful answer. You can ask a lot of people actually ask me a lot of questions, right? And they got very helpful answers. So yeah, if you study, I'm pretty sure you can get a very good grade out of this course. You just have to study. That's the only requirement I have for you. Okay. And yeah, the material, except for the last problem, the graduate problem. Every problem on the, and maybe 13 part A. Everything else were the things we have talked about. Maybe also 11 part A a little bit, but there was an exact example in the book. If you had studied a little bit, you could have seen that example. I mean, even if with control F-ing, you could have found this example for part A to answer the exam. Okay. But for the next exams, we are going to shorten the exam, the number of problems. Probably like 10 descriptive problems as the same as this one, but 2 problems for undergrad and 3 problems for graduate students. Okay. And a little like problem 1 here on this test was pretty extensive, right? If I had to, for the next exam, if I were to ask you to calculate circulations, that will be the only part of a question. Okay, you won't get a 3-part question. And let's see if we have any questions from the online students. Yeah, we have one. If you do the exam online, can you provide a scan of the graded copy to us? Okay, so we have one question. I did not grade it by pen, but I commented the exam in the exam portal. So if you submit online, if you click on the exam, you will see my comments in a box. If you have further questions, we can discuss the specifics. You can send me an email. I'll send you the specifics of the problems with your exam answer. So is there any questions? No. None. Was there any problem on the exam that you don't understand, you cannot solve? Except for that, I know one problem we had. I will talk about that problem. Other than that, yes. 13A, sure. What else? Oh, okay. Then we have to spend all of this. All of what? All of the problems on the exam? No, the work one. Oh, okay. Yeah, we can definitely do that. I guess we keep it. There's no harm in spending the class on solving these. Okay, so let's actually do all of them. Okay, if you want to do just a couple of them, let's do all of them. So first question: is there any question about the grades or policy or the exams or anything, the homework, before jumping into the solution to this problem? So first question. If not, then yeah, you don't have any questions here as well. Explain how can one investigate whether a flow is an incompressible flow field. The only answer I was looking for here was this. Divergence of velocity has to be 0. That's it. So for an incompressible flow field, the idea was time rate of change of velocity, volume, which is the divergence of velocity, has to be 0, which essentially means that your conservation of mass equation, total derivative of rho v, which is total derivative of rho v del rho, right? Or let's do del rho v has to be, this is your, do you see this on the board? I don't think so. Let me use a different color. I don't know why they don't clean these boards. So this was the conservation of mass equation for an incompressible flow field. This part has to be 0. We can take the rho out of this part and then conclude that divergence of velocity has to be 0. Okay? But the only answer I was looking for was this. Divergence of velocity has to be 0 for an incompressible flow field. What is the main characteristics of an incompressible flow field? The volume of your contour volume, whatever that is, does not change, right? Which essentially means that your density is going to remain constant. Okay, next part, next question. Consider flow over a flat plate, a flat plate airfoil that has a length of 2 meters. The shear stress resulting from the skin friction on the surface was found to be, this can be a tricky problem. So we are given the shear stress, du dy at the wall is 10 pascals. Okay? And the length or the chord of the airfoil is 2 meters. So the question is, what is the drag force per unit width? Okay? So that's the first thing you need to find here in your mind is that what is drag force per unit length? What is the unit of drag force per unit length? We're talking about the force, so newtons, and it is per unit length, so newtons per meters. That's the unit. We are looking for something that's in newtons per meters. And it's a multiple choice question, so you look at the numbers. Part C, the choice C is the wrong choice because it's only in newtons. But we don't know anything about choice A, B, and D yet. And so let's look at the givens of the problem. We are given the meter, the length of the plate, and we are also given the stress, right? How can we find the force? Force is your stress multiplied by the area. Here we are looking for a per unit length, so your stress multiplied by the length. So 2 multiplied by 10, 20 newtons per meter, which is answer B. Okay. Number 3, what is the center of pressure? Why is it a good idea to use a point like this in aerodynamic force analysis? Center of pressure. Center of pressure is a point at which sigma of m is 0. So there is no moment applied to that force. That's essentially the point at which where your forces pass through. That's the definition you had in fluid mechanics, right? Center of pressure is a point at which your forces pass through. Why is it a good idea to use a point like this in aerodynamic forces? Let's see. Who can tell me that? So we know what center of pressure is. Why is it a good idea to use this point for aerodynamic force analysis? Because there's no moment. You only have the forces. Forces pass through this point. That's it. Okay, so question 4, what are elementary flows? So the answer I was looking for here, a lot of you, have correctly mentioned that these are very simple types of flows, but most of you failed to mention that the Laplacian of a stream function or the Laplacian of the velocity potential, if any of those exist, has to be 0, right? So simple flows plus Laplacians has to be 0. What are the examples of them? Name the main ones. We had the uniform flow, we had the source or sink flow, we had the doublet flow, we had the vortex flow, right? And how can we build a more complex flow using elementary flows? Just add the stream functions or velocity potentials, right? That was the idea. Okay. Question 5. How can you find the speed of sound at any location? I was looking for one equation here. A speed of sound is equals to a square root of gamma RT. Some of you have used the gamma R divided by MT. It's essentially the same thing. This is the universal gas constant. This is the specific gas constant. So this is for air. This is for that 8.31, for whatever that number is. That's the universal one. But you just have to divide by the mass, molecular mass. What else was this? What does the speed of sound signify? It's the speed at which your pressure waves or sound waves move through a medium, any medium. Define path lines, streamlines, streak lines. And is there any condition in which the 3 lines will be the same? This one was very surprising to me that some people didn't get right because we had 3 separate slides in the lecture notes dedicated to all of this. So just could go there and just copy the lecture notes. So path lines is the path that a particle takes to go from point A to point B. Right? A streamline is a line that has the velocity is tangent to that streamline, right? And a streak line is a locus of all points that pass through all of the particles that pass through a point A at like time delta t. What is the condition for them to be equal? A steady state, right? This also was a part of the lecture notes. What is the main characteristic of the rotational flow? Kerr law velocity cannot be 0. What is the D'Alembert paradox? Okay. Let's do an audience question. What is the D'Alembert paradox?
It's when you have to say that the drag is equal to 0, the drag coefficient, even though there has to be drag in order for there has to be friction to rotate that object.
Okay, so for a flow over a cylinder or this type of flows that you will see that there is some drag. Your flow is pushing back your cylinder or whatever. You will find 0 drag with implicit assumptions, which essentially means that the D'Alembert paradox tells you that viscosity is the cause of the drag, right? And if you don't consider it, you will get 0 drag for some cases, right? Okay. So number 9, explain the mechanism behind the formation of body layer close to a wall. The idea here is that the fluid layer adjacent to the wall is going to lose all of its momentum to the wall, right? And this momentum loss, this momentum deficit is going to transfer to the other layers. That's why you are going to see a velocity gradient because of the momentum difference until your velocity gets to 99.99% of your free stream velocity, and that will show your body layer thickness. Okay, so mechanism is momentum loss of the fluid layer adjacent to the wall. And some of you actually mentioned no slip condition. No slip condition is the condition at which your velocity at the wall is going to be 0, right? That's just the boundary condition. That doesn't necessarily define the body layer. And what are the important drag force calculation? Friction drag, right? If you don't have body layers, you don't have friction drag. That's one answer, but we also talked about the D'Alembert paradox, viscosity, body layers, all of those things contribute to the drag calculations in general. And we're going to see later on that viscosity is actually how an object, how nature, let's put it this way, how nature is going to talk to the body in general, not just for drag, also for lift calculations. Okay. Is there any questions so far? No. Okay. So the last part is this. Can we safely assume viscous flows are irrotational? And this was actually in the lecture notes as well. And there was a huge no in the lecture notes. We had the same question. There was a huge no in red in the same lecture note. And the reason that we had a picture in that part of the lecture note for the reason of why viscous flows cannot be rotational. So the shear stress, you are going to get shear stress in 2 opposite directions on a fluid particle, which essentially means that you are going to have some rotational forces. It doesn't really mean this is rotating. There is a rotational force being applied to it. Okay, so the flow is not going to be irrotational. Kerr law velocity is never 0. Okay. Any questions about the descriptive problems? So it's actually a good thing that we are solving this, because I saw a lot of you were still working on this at the 45-minute mark of the exam. And I expected this to take you 10 minutes, right? And I kept saying it in class. If it's taking you more than 10 minutes, then you are doing something wrong, right? Just leave it and go to the next questions. So again, for the next exam, if you are spending more than 10 minutes on the descriptive problems, then you don't know the answer. Just leave it, go solve the problems, right? And not knowing an answer is also acceptable. Not everyone has to get 100. I mean, most of us don't get 100. So as long as you are getting, you're understanding the whole concept, and getting a decent grade out of the course, you should be fine, right? Okay. Any questions so far? No? Okay. So, first problem. Given an incompressible steady flow where the velocity is this, v is x squared y minus xy squared in the I direction plus y cubed to the third minus xy squared in the j direction, in the y direction actually. Does the velocity field satisfy the continuity equation? What should we do here? What is the continuity equation? Does anyone? I know you do, but someone else. Continuity equation. What was the answer to the first problem?
Del P, del T plus del X, like rho U plus del Y, rho V plus del Z, rho W.
So you're talking about that del rho dt, right? The partial rho, partial t, not partial p. You're talking about the conservation of mass, right? But we're talking about the continuity equation, which is a simplified version of the conservation of mass. What was the answer to the problem number 1? We just had it, right? Just go back to problem number 1, give me the answer. Exactly. Divergence of velocity is 0. That's your continuity equation. So for an incompressible flow, conservation of mass becomes continuity. Divergence of velocity. Okay. How can we calculate this? That's del operator, the dot product with v. If you don't remember how to calculate this, you can, as long as you know what is this vector, this del vector, you should be able to just plug it in and find the dot product, right? What is this del operator? Partial x I, partial y j, and partial k of course in Cartesian coordinate system, right? This is this vector, and we're going to find the dot product with the velocity vector, which is ui vj plus wk, right? Dot product is going to be equal to this multiplied by this, plus this multiplied by this, plus this multiplied by this. So partial u, partial x, plus partial v, partial y, plus partial w, partial k. This has to be equal to 0. So if you didn't remember the dot product, this is how you do the dot product. Just multiply each component of the, yes. That's partial over partial k. It's this specific question is a 2-dimensional question, so that part is going to be 0. Okay.
The K should be Z.
Yeah, I'm sorry. That's what you meant then. I'm sorry. Doesn't matter what the name is, but you are correct. And correct, the common naming scheme is Z. I'm sorry about it. And here we have to have K for the vector. IJK. Okay. So does the velocity field satisfy the continuity equation? This part is 0. Partial W, partial Z is 0. And let's take the derivative of this part. Partial U, partial X is the derivative of this with respect to X. So we're going to get 2xy minus y squared. Okay? And partial V, partial Y. Partial V, partial Y, that's the derivative of this with respect to Y. So you're going to get 2y squared, or y squared, sorry, y squared minus 2xy. We'll cancel each other out, and you are going to get 0. So it does satisfy the continuity equation. Okay. The next part is asking us, does a stream function exist? If you recall from the conditions for an stream function, the velocity field had to be a two-dimensional field, which it is. Also, the continuity equation had to hold true. So, yes, because it's a 2D, incompressible. The continuity equation holds true. Stream function. But how can we calculate the stream function? That's the next part. Calculate the stream function. Right? In the homework that we had, I gave you the stream function and asked you to find the velocity. Right? Here we are doing it in reverse. Okay, so how does the two components of velocity, how do these two components of velocity relate to a stream function? U is equals to partial psi, partial y, right? Negative partial psi, partial x. That's in Cartesian coordinate system. Right? We are all doing it for now. We are in Cartesian coordinates, which essentially means that your psi, you can have two equations for psi. Psi is going to be equal to integral of u dy and integral of v dy. And these v's here are a small v's, right? So the component of velocity in the y direction. Okay. So these are just linear integrals. Plug u in there. That's the integral of x squared y minus x y squared dy. X squared y minus x y squared dy. This will give you what's the solution to this integral? It will be x squared y squared divided by 2 minus x y to the third divided by 3, right? Plus a constant as far as y is concerned, right? This constant can still be a function of x, though, right? So we are going to make it more general and write f of x. Because velocity is a function of both x and y, which means that stream function can be or is a function of both x and y. So if we take the derivative of this with respect to y, we are going to get to this component of velocity, and this f of x, when you take the derivative of f of x with respect to y, it is 0, right? As far as y is concerned, that part is 0. So let's take the derivative for this other part of the integral of v dy, integral of y third. There's a negative. It's a negative, and it's the negative integral of v dy. So y third, y to the y cubed divided by 3 xy squared dx. So this is going to be, there's a negative sign, so we have to bring in the negative sign. Negative xy3 to the 3 minus x squared y squared divided by 2 plus f of y. Okay, so that part, the constant can be a function of y. That's the idea. And now let's compare the two results. This one is a plus sign. These two are identical to each other, which essentially means that this f of x and f of y is just a simple constant. Can be 1, 2, 3, 1,000, 1 million, whatever, right? And you can make a conclusion for your stream function to be x squared, y squared divided by 2 minus xy to the third divided by 3 plus a constant. This constant this time is a number, just a number, okay? So that's part A. You have the solution. Part B is asking us, yes. That's not the condition for a stream function. That's the, okay. We'll talk about it. That's actually, that's a mistake some of you made. And I also, because this has happened before, I also mentioned this in class. And it is not a bad idea to mention it again. So what is the condition you are mentioning? This is the condition on a stream line, okay? Not a stream function. These are two different things. A stream function and a stream line are two different things. We actually use this to find the slope of the line of that stream function. If you rearrange this, what are you going to get? V dx is equal to u dy, right? And dy dx is going to be equal to v divided by u. So if you take this, you will find the slope of the stream line, right? A stream function is concerned with the mass that is passing through between two stream lines. One streamline, yep. So if I tell you to find the equation of a streamline, this is the first step for you. You find the slope of that line, and then you just do a curve fit. Okay? I mean, you have the slope. You can, as long as you have 2 points, you should be able to find it. But yeah, so this is the streamline equation. That one is a stream function. Make sure not to make this mistake. So next part B, does a potential function exist? If a potential function exists, what is it? How can we determine whether a potential function exists or not? Your flow has to be irrotational. So curl of velocity has to be 0, right? That's the condition for velocity potential. For a stream function, condition was 2-dimensional and continuity. For velocity potential, in addition to those, you have curl of velocity. So you calculate the curl of velocity. If that's 0, then you have to find the velocity potential through the first type of, same type of analysis, okay? Let's do this first. How can we find the curl of velocity? We have to take the determinant of this matrix. Okay, it's a 2-dimensional system, so we already know that the I and j parts will go to 0, and we are only going to get the k part. So partial v partial x, your curl of velocity, partial v partial x, is going to be equal to partial v partial x minus partial u partial y, right? Is this 0? Partial v partial x is going to be, this part is 0, derivative. This part is negative y squared, right? Partial u partial y This part is 2x. This part is only x squared, and then this part is 2xy. So Kähler velocity is not going to be 0. Does it make sense? So potential velocity potential does not exist for this flow. That's it. That's your answer for part B. And part C, we are told for the region shown below, find the circulation using the two different methods. Okay, so we have this triangle shape that goes to 1 and 1, and then we have y equals to x on one side. Let me ask you one question. What coordinate systems suits this problem best? Which coordinate system? Cartesian. Why Cartesian? I mean, we can have x and y coordinates, but have a circle, right? Yes. Because of the straight lines, exactly. So whenever you see straight lines, you need to deal with Cartesian. You can definitely convert everything to cylindrical, but you will make your life miserable, right? So, and a lot of people actually have done that for some reason. Okay, so we want to take this line integral, VDS. The idea was we have to divide, we have to find different sections. How many sections do we have here? 1, 2, 3. So what is the velocity of part 1, V1? On the line 1, your x goes from 0 to 1, but your y is 0, right? We can see that on line 1, that's the condition. So let's plug y equals to 0. X is the thing that's changing, y is 0. 0, 0, 0, 0. What does it mean for velocity? Your velocity is 0. So it doesn't really matter what your ds is, but your ds is also dxi, right? dy is, there is no change in y, so di is 0. But the integral over the surface 1 is 0 because your velocity is 0. Okay? V2. What is happening on V2? Your x is always 1. Your y is changing from 0 to 1. So let's plug x equals to 1. You're going to get y minus y squared and y cubed minus y squared. So y minus y squared I plus y cubed minus y squared j. What about the ds? X does not change, so that part is 0. Your ds is going to be dyj. So the integral here on surface 2 is going to be equal to, since we only have the j part present in ds, we only have to take the integral of the j part. Y cubed divided by 3 minus y squared dy. That's the integral of part 2. The tricky part of this problem is the line 3, right? So what is happening on line 3? We are told the condition on line 3 is that y is equals to x. Okay, so let's plug that in. Y equals to x is going to result in 0i, so u is going to be 0. And what about here? You're going to get y cubed divided by 3 minus y cubed. So you're going to get negative 2y cubed divided by 3, right? Does that make sense? 0i plus negative 2y cubed divided by 3j. Okay. What about ds? ds, x is equals to y. So we can have di I plus dyj. The thing is, since we only have the j part of velocity, we don't need to use this part at all. And your integral is going to become negative 2y cubed divided by 3 dy. So you have the two-line integral. What is the integral of 2y cubed divided by 3?
We can take out 2 divided by 3, and we have 5 in the power of 4 divided by 4.
That's it, exactly. So essentially, then 4 will cancel with, you can actually, let's not do that. So eventually, you're going to get 2 by 3 divided, and the two negative signs will cancel out. y4 divided by 4. And here, your y is changing from 1 to 0, which essentially means that your final solution is going to be negative 2 divided by 12. Right? You apply y1, you plug in y1 here, which is 0, minus y2. Right? Negative 2 divided by 12. If you take the integral here, you are going to get y to the 4th divided by 12 minus y to the 3rd divided by 3, right? Which is going to essentially be 4y to the 3rd divided by 12, right? And those, you can take that, you can subtract them from each other. You're going to end up with 3 divided by 12. Okay, negative 3 divided by 12. So negative 3 divided by 12. And there's also another negative sign here. Should go in and make the final integral positive. And eventually, your circulation is going to be the sum of all of these integrals. The first integral is 0. Second integral is 3 divided by 12. Third integral is negative 2 divided by 12. So your circulation is going to be equal to 1 divided by 12. Okay? Does it make sense? Yes.
What happened to the minus x y squared in that integral?
In which one?
In the integral to sub 3.
Okay. So the idea was x is equals to y, right? So when you, instead of x, if I plug in y, I'm going to get y cubed here minus y cubed. So they will cancel out. Okay? So, and the next part is asking us to find the same value, essentially using the Stokes theorem. The double integral of curl of velocity dA, or ds as a d area. Okay. So curl of velocity, you actually, I assume in the exam, you already have calculated the curl of velocity, which was partial v partial x minus partial u partial y, right? Partial v partial x partial u partial y. If you take this derivative, partial v partial x is negative y squared minus partial u partial y is going to give you x squared plus 2xy. Okay. So this is the curl velocity. We only have to plug it in here, and take the integral, double integral. The other thing we need to address here is also dA. dA is dx dy. That's the area of a very small element inside this triangle, which has the length dx, length dy, dx dy. In Cartesian coordinate system, your dA is always dx dy. Doesn't matter. Can be dy dx. Should give you the same result. If it doesn't, then you are doing something wrong. Okay? So essentially, that will change the order of the integral. If you do dy dx, you are going to take the integral first from y instead of x. If you are doing an indeterminate integral, it doesn't really matter. As long as you plug in the boundaries, you should be fine. But we are doing a determinate integral. Everything goes from 0 to 1. Okay? Yeah. So you plug in the values, you take the derivative. Let's negative y squared, x squared plus 2xy dx dy from 0 to 1, 0 to 1. There is something you can also do to make it a little maybe simpler. You can take the first integral, because both of them go from 0 to 1. To make it a little simpler for yourself, you can take the first integral from 0 to 0 to x, right? It should give you the exact same result. Yeah. Okay, so take the integral with respect to x. I'm going to write it down here. Negative y squared x minus x cubed divided by 3 plus x squared y from 0 to 1. And plug 0 to 1 here. You're going to get the value, negative y squared y to the third. And there's also a negative sign behind the integral. Just make sure you are. So this is, let me actually write the correct form. Integral from 0 to 1 dy. There's also a negative sign outside of it. So this integral is going to be equal to y squared plus y dy. Plug this in. Is going to be y cubed divided by 3, 1/3 y plus y squared divided by 2. If you plug the numbers in, it should give you 1 divided by 12 as well. Okay. And I mean, as there are a couple of people who didn't get the exact same result, which as long as they mentioned that I know I understand I have to get the same results from these two integrals, I only deducted 1 point out of the 20 or 25 for undergrads. Okay, so that's problem number 1. Let's do, or 11. Let's do problem number 12. Problem number 12, the velocity field for the fully developed viscous flow in a duct. That's the Hagen-Poiseuille flow, very famous type of flow, and is as follows. So it's only a one-dimensional flow. Okay? Only a one-dimensional flow. U is equals to 1/2 divided by 2 mu dp dx y squared minus h squared divided by 4. And v and w are 0. dp dx is the pressure gradient along the x direction, is a constant. So I saw a lot of you were struggling with seeing dp dx, but the problem is telling you this is a constant. You don't need to worry about it. It's just a number, right? It is in the form of the derivative, but I'm telling you that this is a constant. You don't need to worry about it. And h is the height or diameter of the duct. Is the flow rotational or irrotational? How can we determine whether a flow is rotational or irrotational? Del curl of V, we have to calculate this. If it was 0, then the flow is irrotational. If it wasn't 0, then the flow is rotational. How can we find this? Again, take the determinant of this matrix. This is still Cartesian coordinate system. So we are using the Cartesian coordinate system formulas. If you were to use cylindrical or spherical coordinate systems, your formula would have looked the same, but the coefficients would have been a little different. You have all of those in your lecture notes and the book. So V and W are 0 here. And the only places you're going to get is where you have partial U, partial Y, and also you're going to get a partial U, partial Z, right? In another dimension. But there is no dependence on Z here in this equation. So essentially, you only have to take the derivative of this U with respect to Y to figure out whether the flow is rotational or not. So partial U. Is this clear? Yes? How we got here? Which is K, right? So let's take the derivative with respect to Y. All of these are constants. Don't matter at all. We are essentially taking the derivative of this. Y squared minus a constant. What is the derivative of Y squared minus a constant with respect to Y? What is that derivative? 2Y. Is this 0? Is 2Y 0? No. So it is not equals to 0. And the flow is rotational. Okay, next part. We just said why it is rotational. Next part is asking us for a dot flow, does the Bernoulli's equation hold true? When we were talking about Bernoulli's equation, and actually you have seen this in your fluid mechanics, hopefully you have seen this in your fluid mechanics as well, Bernoulli's equation only holds true for incompressible, inviscid, and steady state problems along a streamline. Okay? So it is possible for Bernoulli's to hold true for a rotational flow, okay, but only along a streamline, not all over. Okay? But we are not satisfying the inviscid assumption here, because you are specifically told that a fully developed viscous flow, which means that your flow is not inviscid. Okay? So no, Bernoulli does not hold true because rotational. So it only may hold true along a streamline, rotational flow, and is viscous flow, so doesn't hold true. Okay. Question number 13. Part A. Let me actually read through it. Velocity profiles are measured at the upstream end, surface 1, and the downstream end, surface 2, of a rectangular control volume as shown in the figure. So we are told that we have a rectangular control volume. Here we are not told that these are walls, just the control volume. So mass can go out and come in. Right? We have an airfoil. C. We have a distribution, velocity distribution, and another type of velocity distribution here. Okay. So, part A, if the flow is incompressible, two-dimensional, and steady, what is the total volumetric flow rate across the horizontal surfaces? Okay? Conservation of mass. Whatever is coming in has to go out. The incoming mass is coming in from surface 1. So m dot 1 has to be equal to m dot 2. And m dot 3 and m dot 4. Right? We are told to calculate m dot 3 plus m dot 4. Eventually, it may come out 0, but we cannot make any assumptions at this point. Right? We have to do the calculations. So, and it's an incompressible steady flow. M1, M is equals to rho AV, or rho multiplied by your flow rate, Q. Okay? So let's plug that in. And this is the thing we are looking at, right? We are looking for. So rho Q1 is equals to rho Q2 plus rho Q3 plus rho Q4. All the rho's will cancel out because incompressible. Q1 is A multiplied by V. Velocity multiplied by the cross-sectional area. You can safely assume that we have a unit depth here. Okay? You don't need to make that assumption because this A is this depth is the thing you are going to use to calculate all of these cross-sectional areas. So that will actually cancel out as well. Right? So the only part that is important is the length. Okay? So we are going to assume that we have already taken that out. So this length is, what is this length? A2h. Velocity coming in is going to be equal to, flow rate coming in is 2h multiplied by your, it's a uniform distribution multiplied by your velocity, right? That's only the area of this rectangle. So we are going to get 2h u infinity is going to be equal to, then Q2 is the tricky part. Velocity is not uniform anymore. So we cannot just simply multiply this by the area. Okay, what should we do? If you recall, Q in general, we defined it as the integral of u in this direction is going to be dy, right? The most general term is integral of u dA, but here we took the depth out because it is going to be the same for all of the surfaces. So integral of q u dy. Okay, from negative h to h. But since the distribution of velocity is symmetric, we can actually take the derivative from 0, if this is 0 to h, and then multiply the integral by 2. Okay, so let's plug that in. That's u infinity multiplied by y divided by h. 2 integral from 0 to h, u infinity y divided by h dy. We can take u infinity out. Integral of y divided by h is y squared divided by 2h. Then you plug h in here, is going to be 2 u infinity h squared divided by h, right? Divided by 2h. So eventually, for Q2, you're going to end up with u infinity h. Okay, so here for the Q's, we have u infinity h, 2u infinity h. What is the flow rate out of surface 3 and surface 4? Take UH to the other side. Flow rate is going to be equal to UH. So essentially, half of the incoming flow is going out of surface 3 and surface 4. Okay? Is this clear? Part B is has asked us to calculate the drag, assuming that we are in a wind tunnel. Okay? We actually had an equation for this, if you recall. Who can tell me what was that equation? That's drag per unit length. Mm-hmm. U2. That's it. And what is the integral with respect to? dy, right? That's from h to b is for that specific problem. So here we are taking this integral from negative h to h, right? Over the y. Again, it is symmetric, so we can actually take the integral from 0 to h and multiply it by 2, rho 2 u2, u1 minus u2 dy. Plug the values in, your u2, we can take the rho out, 2 rho, we are told it is incompressible, integral of u infinity y divided by h minus u infinity multiplied by u infinity minus u infinity y divided by h. We can take the u infinities out as well, dy. So your drag per unit length is going to be 2 rho u infinity integral of 0 to h. And then I'm going to multiply this y by h, y divided by h, by the whatever we have in this parenthesis. We're going to get y divided by h minus y squared divided by h squared dy. Taking this integral, that's 0 to h. Taking this integral is not that hard, right? The integral is going to be y squared divided by 2h minus y cubed divided by 3h squared from 0 to h. So plug h in, you're going to get h squared divided by 2h, so h divided by 2 minus h cubed divided by 3h squared, so h divided by 3, which essentially means that you are dealing with h divided by 6, right? So drag per unit length, 2 rho u infinity, can actually bring the 2 here there as inside there as well, divided by h, multiplied by h divided by 3. Any questions? If there's no question, let's solve the last one. See, you had enough time. Let's solve the last one. Last one is actually a bit tricky, so I didn't really expect the graduate student to have an easy time with this. But except for we have 14 graduate students in class, including the online and in-class students. Only 3 students solved this. 5 or 6 students solved this, maybe even a little more. 7 students, 7 or 8 students. Let's go with 7 or 8. But only 2 of them got it correct. Okay. So you are to design, I don't know how to pronounce this word, but it's essentially, it's a type of hut to serve as a temporary housing near the seashore. This hut may be considered to be a closed no-leak semi-cylinder. So we have a semi-cylinder, okay, whose radius is 5 meters. 5 meters. Mounted on tie blocks as shown in the figure. We want to neglect the viscous effect and assume the flow field over the top of the hut is identical to the flow over the cylinder. What does this tell you? This tells you that your V on the cylinder is only V theta, because we have already calculated this in class, right? Flow over the cylinder, and we only have V theta, and that would be equal to 2u infinity sine of theta, where theta starts from here, right? This is something we have calculated in class. Okay. So we have seen in class. So you had it in the lecture, no? When calculating the flow over the surface of the air under the hut is at rest, and the pressure is equal to a stagnation pressure P of T. So we are given the stagnation pressure here. P of T. Okay, what is the lift coefficient and the net lift force acting on this hut? We are also given the wind speed, U infinity, as 50 meters per second. Lift coefficient and the net lift force. And the static free stream properties are those of the standard sea level. Okay. Any ideas? Let's see if we have any ideas. We want to calculate the lift and the lift coefficient. If you recall, lift was the summation of all forces in the vertical direction. So for lift, let's do lift first. Sigma, let's say this is y, and this is x. Sigma f of y is equals to 0. We don't have any viscous forces. We don't have any gravitational forces. So essentially, we only have the pressure forces, right? Okay. So what are all of the forces in this y direction? We have the pressure that is being applied on top here. And we also have pressure on the bottom. Okay. What are the forces we have here? We have one force on the bottom, one force on the top. How can we calculate the pressure force on the bottom of this? You are given the stagnation pressure, right? The first thing you need to do is to find the static pressure, right? Because that's the pressure we use in the force calculation. That's it, yeah. Yeah. Yep. Exactly. So your static pressure is going to be equal to your total pressure or stagnation pressure, which is, we are going to assume it's a given value, minus 1/2 rho v infinity squared. You can find this value. What is the total forces here? It's a circular hut, right? Pressure is going to be the same that's being applied here. So we have a uniform pressure distribution. We want to calculate the pressure force. How can we do that? How can we find the pressure force with having the area and having the pressure, uniform pressure? Pressure times the area, that's it. So you multiply this by pi r squared, whatever that is, you are going to get your pressure force in this direction. Okay, that's. But we want to find the pressure on top here. Let's say this is P infinity. Okay. To find the pressure at each point, we have to write the Bernoulli's equation here, between here and any point in the film. So P infinity plus 1/2 rho U infinity squared equals to, that's an arbitrary point 1. Is equals to P1 plus 1/2 rho V1 squared. What is this V1 squared? 2U infinity sine of theta of that point, which is this. Okay? So let's rearrange this. We are going to get P1 is equals to P infinity plus 1/2 rho U infinity squared minus 2U infinity 4U infinity squared sine of theta. So you have the P1. That is given. And then how can we calculate the total force? We have the pressure at one point, and we have the area, but the pressure is changing here. So we have to take the integral of pressure with respect to a small element of area in the surface. And this force has two components. It's going to have two components. We are going to need the component in this direction, which is going to be, you have to multiply it by the sine of this theta. So you plug the values in, and then you do the calculation. The force on the bottom minus the force on the top is going to give you your lift. That's it. And for lift coefficient is defined as, that's the force coefficient, L divided by Q infinity S. You could actually start from pressure coefficient as well, because we did calculate the pressure coefficient in the class. And yeah, so Max is actually pointing to another correct method, but taking this integral would have been a little more cumbersome using that formulation. I mean, not really, but you just had to make sure that you are taking into account the P infinity as well. Okay. Is there any questions? Yes.
We find P1 using Bernoulli's equation, and we use that P1 in that integral to then find left.
To find the forces on top of the cylinder.
Where are you using that original P that we got up on the top?
That's for the forces on the bottom. We have two forces, right? Forces on top using this integral. Forces on the bottom, just force pressure multiplied by area.
Okay, so we get those two forces.
And then you just subtract them, where they're in different directions. You have the lift. Any other questions? See, we solved it in 1 hour. So I guess you had enough time. But OK, so again, if you are not satisfied with your grade for whatever reason, what I can do is to use your final grade for this exam. And what I have to think about this a little more, but what I also can do is to use that part of final grade that is from chapters 1 to 3 for this exam. So only exam 1. Does this make sense? So the questions on final grade which are from chapter 1 to chapter 3 will account for your exam grade here. I think that will be a little more fair. But yeah, I think that's a better idea. But so the point is, you can get 100 out of exam 1. You can still get 100 out of exam 1. Okay. But on the next exams, you will be only allowed to bring in a letter-sized, two-sided cheat sheet. Right? No Google, no computers, no books, no nothing. Right? And online students have to be online during the exam. They have to turn on their cameras, unless there are dire circumstances. And we will work on those on an individual basis. If you don't have any questions, that's it for the class. I wanted to start chapter 4, but I guess it wasn't a bad idea to go over the exam. We will start chapter 4 on Wednesday. And good luck.
You said that we have to return the exam?
Yes, if you don't need it. Yeah.
So do you want to?
Okay.
You want them right now?
Yeah, why not?
I have a couple questions.
Sure.
First off, I think you did the math wrong.
Okay.
Online, I was missing